We're right in the middle of this massive, incredible shift to cleaner energy, right? Solar panels, wind turbines, they're everywhere. But this brings up a really big question. As we keep plugging more and more of these green sources into our power system, is our old-school electrical grid actually ready to handle it? Okay, let's really dig into this.
And that really is the heart of the issue, isn't it? Our ambition for clean energy has just been moving at lightning speed, but has our critical infrastructure, the actual wires and poles, kept up with that pace? It kind of feels like we're trying to run some brand new, super fast software on really, really old hardware.
This is a perfect way to picture the challenge. Think of our power grid like a network of streets and highways. Now, imagine it's a super sunny day and thousands of solar panels all start pumping out power at the exact same time. It's like a flash mob of cars all trying to get onto a tiny neighborhood street at once. Total gridlock. The system gets overwhelmed, voltage spikes into dangerous territory, and things start to break. The solution? Well, it's basically like installing a super smart, AI-powered traffic control system for all that electricity, one that can manage the flow and keep everything running perfectly smooth.
And here's something that might surprise you. It's about where the biggest problems are happening. According to the U.S. Energy Information Administration, a staggering 40% of all energy loss happens in what's called the distribution grid. That's the final stretch of wires that brings power directly to our communities, to our homes. That's an enormous amount of waste we just have to get a handle on.
So the big goal here is to teach our grid to be, well, smarter, to be more adaptable. The official name for this mission is Volt VAR Optimization, and it's all about creating an intelligent, self-balancing network that is not only stable, but also way, way more efficient.
So what in the world is Volt VAR Optimization, or VVO?
Honestly, the best analogy is to think about the water pressure in a huge city's plumbing system. If that pressure, which is like our grid's voltage, gets too high, pipes can burst. Not good. If it's too low, you barely get a trickle from your faucet. VVO is like the master control system that makes sure every single point in that entire network has exactly the right amount of pressure to work safely and without wasting a drop.
And VVO is really on a two-part quest. First, and this is the most important, is safety and stability. It's constantly working to keep the voltage within a very tight, very specific safe zone. This protects all of our electronics and prevents catastrophic blackouts. The second part is all about efficiency. By optimizing that flow, VVO can drastically cut down on all that wasted energy we were just talking about, and that directly means lower electricity costs for all of us.
Okay, so that all sounds great in theory, but how do we actually do it? Well, the solution begins with the physical hardware, the actual real-world tools that grid operators use to manage the flow of power.
First up, we've got capacitors. A good way to think of these is like little localized reservoirs of a special kind of energy called reactive power. Now, this reactive power is absolutely essential for running big things like industrial motors. By placing these capacitors in strategic spots, we can take a lot of the strain off the main system, which boosts efficiency and frees up more room for everyone else.
Next, we have smart inverters. And this is so cool because this is where renewable energy gets to be a part of the solution instead of being the problem. The smart inverter is the brain that connects a solar panel or a battery to the grid, and it can be commanded on a millisecond's notice to either provide or absorb that reactive power. This turns every single solar installation into an active, helpful player in keeping the entire grid stable.
And finally, there are synchronous condensers. Okay, this is genuinely fascinating. Old-school power plants have these enormous, heavy spinning turbines. All that spinning mass creates physical inertia, which naturally helps the grid resist any sudden changes. But as we shut those old plants down, we lose that built-in stability. Synchronous condensers are basically huge rotating machines that don't actually generate power, they just spin. They're there to add that crucial, stabilizing inertia back into the system so it doesn't become fragile.
So, having all this amazing hardware is kind of like having a world-class orchestra full of brilliant musicians. But you still need a conductor to make sure everyone is playing together in perfect harmony. And that is where the brains of the operation come in.
I mean, just think about it for a second. You have thousands, maybe millions of capacitors, smart inverters, and regulators all over the grid. The demand for power is changing every single second. How could a person possibly coordinate all of those pieces in real time to keep everything in perfect balance? The answer is, they can't. It's just not humanly possible.
So we turn to a very special type of AI called deep reinforcement learning. It's actually the same kind of AI that's been trained to master incredibly complex games like chess and Go. We basically turn the power grid into a giant video game for the AI. It tries out different moves, like flipping a capacitor on or telling an inverter what to do, and it gets points or a reward for good outcomes, like stable voltage. And it gets penalized for bad ones. It learns by playing.
And it's not just one big AI trying to do everything. It's more like a team. What you're looking at here is a model where multiple AI agents are each in charge of a different part of the grid. They all watch what's happening, they take coordinated actions together, and they all learn from the same shared reward system. It's a distributed intelligence, all working towards one single goal, a perfect grid.
And we actually know it's working because we can literally watch it learn. This graph shows the AI's score over thousands and thousands of practice runs. You can see at the beginning, down on the left, is making a lot of mistakes and getting these big negative scores. But as it keeps playing and learning, the reward score steadily climbs up into positive territory. This is the proof that it's actually mastering the game of controlling the grid.
Okay, so the theory sounds amazing, right? An AI that learns to run the grid. But what does this actually look like when you put it to the test? Let's take a look at the results from testing this AI on incredibly realistic grid simulations.
This right here is the money shot. On the left, you're seeing the voltage across a grid with a ton of solar power and no smart control. It is a complete mess. You see all those dots outside of the red lines? Those are dangerous voltage violations. Now look at the right. This is the exact same scenario, but with the AI in control. It's perfect. Every single point is brought back inside the safe zone, and it does it in milliseconds.
And the hard data absolutely backs this up. When the researchers threw thousands of really tough scenarios at the AI, it achieved a success rate that's practically perfect. On a really complex grid simulation, what engineers call a 12-3 bus system, it fixed the problem 99.975% of the time. I mean, that's just incredible. And it means less wasted power, lower bills for us, and a grid that can handle way more green energy.
Now, of course, to make all of this magic happen in the real world, you need everyone to be playing by the same rules. You need a universal rulebook. And for the smart grid, that rulebook is called IEEE 1547. It's basically a standard that makes sure a smart inverter from one company can talk to an AI controller from a totally different company, and they can all work together safely. It's the technical foundation that makes this future grid possible.
And I think this quote from the researchers who actually developed this AI system, it just sums up the whole thing perfectly. They say they've created a system that lets the grid self-learn with the cognitive function by mimicking the human mind. We are literally building a grid that can think.
So really, the big takeaway here is that the technology to create a smart, self-healing, and incredibly efficient grid, one that can easily handle a 100% renewable future, it's not science fiction. It exists right now. The grid is learning to think for itself. And that leaves us with one last really exciting question. What are we going to teach it to do next?